Hello and welcome to our webinar, Test Automation for Motor Control Systems. I'm Thomas Schütz and I'm the CEO of Protos, and I'm going to use the mini-hill to demonstrate you a little bit about the test of motor control systems. So let's start with the motivation. Why are we doing what we're doing? The main reason is we want to be faster, we want to learn earlier, we need to test earlier. So what we essentially do is we bring the integration and the system test, or at least part of the system test, to the implementation, to the desktop of the developer, or to the continuous integration for a really fast response time. So any change you make, you want to test within minutes instead of weeks or months. So that's the basic motivation here. So let's have a look at the normal development process of an embedded system. For example, you start on an evaluation board, you configure your drivers, you start with your hardware-related software components, with the motor control, with the battery control, with low-level bus systems, CAN, LIN, and so on, and protocols sitting on top of that. Then in the end, you do your software components with your application logic, and you integrate everything to an application. The normal points where you usually test are here. So for the pure software components, you can run unit tests, usually not for everything, especially, for example, for a motor control. It's really hard to test the motor control with a synchronous unit test. You need a little bit more for that. And later in the process, you can run a hardware-in-the-loop test or a system test. That's usually very expensive, very late in the process. It's necessary, of course, it's good, but it's very late in the process. So for the most part, for the most time in your development, you do not have a real test automation. So that's exactly where we place the mini-hill. The idea is to test everything on an evaluation board, on the real processor, your complete software stack, including the complete software, application software, hardware-related components and drivers. So what do I really want and need? You want to test what's changed most frequently, and that's your software. Now you change your motor control system and you want to test your software. Your hardware is not changed more often than, let's say, once a month, or later maybe every 3 or 4 months. So you do not need to test your hardware every time you change your software, but your software might change 100 times a day. So what you want is, or what you need is to test every code change of every developer within minutes instead of weeks. It's also good to have a full regression test, because you change something at one place and you have effects maybe at the other side of your project. You have shared resources, you have limited resources, you have the same memory space, so there are all kinds of side effects your changes might have on other code parts. Another point is you should use continuous integration in the long run to enforce the tests and to save time, because it's even if it's automatable on your desktop, you want to test every change of every developer, and can be done really good with continuous integration. In the end, you need a hardware-in-the-loop test, an automated hardware-in-the-loop test, because it's more than pure software units. For example, your motor controller, that's really hard to test as a software unit test. So why is it so hard to test an embedded system, or why is it so hard to automate tests for embedded systems? Let's have a look at a typical motor control system for an oil pump. In this case, it's safety relevant. We want to test a temperature shutdown for 300 relevant system states. That's a real world project. Before, the customer had a climate chamber with the complete electronic control unit, with all the sensors, with power electronics, with the motor, with a pump, with a hydraulic system, and so on. The test automation was done via script, but the problem was that this test, first of all, this test would have taken 30 days execute more or less, because a climate chamber is really slow. And the other point is it never really worked automatically, because you can imagine the hydraulic system can fail. You start your test, and after 2 days maybe, or after 1 day, the liquid is out, or the liquid gets frozen, and all those things lead to a real big problem for test automation. What we did, we took out the microcontroller of the system with the complete software stack. We built an environment simulation for the motor control, for all the sensors, actuators, and so on. And then if you have simulated the environment, you can bring the software into any state you want. You can break a PWM signal. You can break all this, the sensors one by one, and have a look at what happens to your system. So it's really good to automate, because there is no hardware except for the electrical signals. And so we got the complete test run down to 50 minutes. That's something you can run on every commit of every developers in a distributed team, for example. So what are the test levels and the test methods you need on the different levels? So let's start with a unit test on the lowest level. So we have a software unit, and therefore you can write a unit test. That's easy to automate, that's easy to do. So please continue doing that. If you have more than one software unit, it's a software integration test. For both levels, you can use a unit test tooling. So that's easy to do. So the next step, for example, if you want to integrate the drivers and motor control system, bus systems, and so on, you can use our mini-hill for basically the smallest possible hardware in the loop test. It's a hardware software integration test at the pins of the microcontroller. The next step is if you include the complete electronic control unit with the sensors, with the actuators, with the power electronics, then you can maybe run a hardware in a loop test, a big hardware in a loop test. That's already really expensive, slow, and really hard to automate with continuous integration, because the equipment is expensive, and so you will always it will never be free for automation, basically. And the last step is a system test. It's necessary to do a system test, of course, but it's even harder to automate. Sometimes it's not, you cannot automate it, and it's really expensive. So it's usually run once or twice during a project, and not after every commit. So from top to bottom, the unit tests are easy to automate with continuous integration. The system test is really hard to automate with continuous integration. So we're sitting here in the middle with the hardware software integration tests. It's not as easy as a unit test to do, but it's also really good to automate. So let's have a look at the typical motor control test setup. So on the right side, you have a system under test, for example, a BLDC motor controller or something like that, or field-oriented motor control. And usually on the left side, you have the motor, and you have all the actuators, sensors, and so on. So if the motor is not attached to your system under test, your system under test fails immediately. So you do not even get to the state where you actually can run a test case. So you need to simulate on the test system the motor and other simulations for a battery, for sensors, and so on. So the motor controls directly the simulated motor and not the real motor. The simulated motor needs to produce the expected sensor signals, and it needs to be usually closed loop, because if you have a controller and you make an open loop simulation, so you make a playback of signals, the controller immediately runs out of scope, and so you can't really work with a closed loop with a closed loop controller if you do not have a closed loop simulation. So instead of the real system, you control the completely simulated system, including the motor, and the the simulation enables a deep and fast testing. And you can always test the happy and the unhappy path because you can make error injection, failure injection, by taking away signals, by letting the simulation misbehave, basically. So whatever you want to test, if you can break it at the interface level or at the simulation level, it's easy to do. So let's have a look at the typical motor control system, in this case a BLDC motor control system in your system under test. You produce 3 PWMs with block commutation. On the left side, you feed it into the plant simulation. The plant simulation calculates the new speed. Here, for example, that's the calculated speed in the motor simulation. And it generates, in this case, 3 Hall signals as digital outputs. Could also be analog values for a single, double, or triple shunt, a field-oriented motor control, or whatever it is. So the real motor is replaced by a simulation, and that simulates really the expected signals. Some simpler simulations you can run with open loop. For example, a playback force for a sensor input like a temperature or something like that, that can be done in open loop. And for most motor control systems, you need a closed loop simulation for a stable control loop. So what can you do with this kind of integration test now? So the main goal is not to test the motor control itself. Yeah, you also test this one, but that's not the main goal. The main goal is to test the motor control integration with the rest of the software system, including all the drivers, the electric signals, all the bus systems, and so on. It's much more complex than just the motor control system. So you can put your system into almost any state you want to test by changing the simulations for failure injection. This enables the complete automation and real speed and depth in your test process. As an example, again, the motor temperature shutdown for our system. So we regard the microcontroller as a black box with the complete software stack you're really delivering in your application. So the right microcontroller with the right software stack. And now you can stimulate from the outside the ADC by providing an analog signal. Then the black box behavior is cascading through your application. And on the outside, I really want to know whether after 100 microseconds, for example, the PWM goes to off because it's safety critical. I need to prove this. And at the other end, I want to know, for example, whether the right error message is propagated over the CAN bus system. So that would be a black box test for the temperature shutdown. And of course, since it's only simulated signals, you can bring the system within milliseconds into any temperature situation you need to test. Examples for this kind of test is, so what can you test? You can, for example, test the positioning. You can run against the block. You can make a fast change of the torque depending on your simulation, of course, of your motor simulation. For a pump, you can simulate a dry run. You can change the viscosity and so on. In general, you can test overcurrents, phase shorts, phase breaks, motor shutdown for any kind of error. You can make shutdown path tests, so trigger for different situations, combinations of situations. You can also make trigger error detection, so via current sensors, gradients, and so on. So let's have a look at certain or specific motor controllers. Already explained the BLDC motor control. The plant simulation usually needs to run between 15 and 30 kilohertz for this kind of simulation. Then we have a field-oriented control in this case. If you're using field-oriented control, you might know what kind of curves those are. We can simulate single, double, triple shunt system. The multiplexing for single shunt is way below 1 microsecond, so it needs to be really fast. The plant model itself runs between 15 and 30 kilohertz. That's a typical frequency. The third example I'm going to show you is a typical DC motor that controls position of something. For example, a position with a spring reset. The plant simulation usually runs between 1 and 20 kilohertz, sometimes a little bit slower. The position sensor in this case could be an analog value or a digital value, a decoder or something like that. So those are typical motor control systems you want to test maybe. How do we do this on a hardware level? On a hardware level, we have our mini hill board. Here you have your microcontroller. That's your microcontroller of your application. In this case, a Cortex M4, an STM32. You put in the evaluation board of your microcontroller. You also can place it next to the mini hill board and use those wires to connect the system under test with your test system. So the pins of this microcontroller are now connected with the test system. And on this side, we also have a Cortex M7, a very fast deterministic processor. And here on this side, you need three things. You need access to the IOs, so digital, analog, SPI, I2C, all the low-level bus systems, and so on and so on. PWM, of course. And the second thing is you need environment simulation, because the test case is not enough. You need to simulate the environment before you can even test something. And then on top of that, you need test cases, of course. So that's everything that has to run inside here. And it's not so easy to develop environment simulation and test cases for asynchronous embedded systems. So that's why we have a model-based development environment for structure and behavior of a test system. So we can create structure and behavior for the IOs, for the simulations, and for the test cases. And then we generate and compile and flash the components or the complete generated components to the test system. So essentially into this processor. In this case, we have another processor we're testing, another system under test. It's an Oryx of Infineon, more for automotive systems, for example. And then the simulation and the test cases run. Why do we run everything on this microcontroller? Because we need it to be hard real time. 20, 30 kilohertz, you cannot run this on a PC, even on a fast Linux RT machine. That's simply not fast enough for a real-time simulation for a motor control system. And also the test cases we run on this microcontroller, because sometimes you want to know whether something happened after, let's say, 50 microseconds or 100 microseconds. That needs to be hard real time. So the test cases are also hard real time. Then we log the results over USB back to your laptop or to the continuous integration server. We transform it into diagrams, because as human beings, we can interpret diagrams way better than textual logs. So we always generate various diagrams for us to make it easier to interpret the results. Then you can close the loop, you can learn, iterate, change your test system or change your system under test and run the tests again. So there is typically response times are more in the region of a component or a unit test. So usually you get response within a couple of minutes, maybe below an hour or so. If you have longer running tests, we always suggest to make 2 stages or several stages, a commit stage that runs after every commit. So you get a fast response within minutes, whether your system works again. And if you have longer running tests, you run them overnight or every 2 hours or at the weekend, or how, depending on how long it takes, whenever you want. So, but the commit stage needs to be really fast. So you get really fast turnaround, you close the testing gap. Yeah. After 5 minutes or 10 or 20 minutes, you still know what you changed. After 3 months, you don't know what you changed, and there are 500 more changes in your system, most likely. So on your desktop, that's the setup on your desktop. That's exactly what I have here. For example, here I have my little test equipment next to me. I'm going to show you this in a minute. And on a continuous integration server, you hook up several boards, up to, I don't know, 20, 30, 50, 100 boards if you want, to your continuous integration server. That's a typical setup in a rack, in a test rack. Here, every mini-hill board runs a different project. Actually, that's our setup for the production tests for our mini-hill itself, but that's exactly what the setups for projects at our customers work. So that way you really can change, you can test every change of every developer within minutes. Doesn't matter where the developer sits. The test setup I already explained. In this case, we have a BLDC motor controller for our example project. It generates 3 PWMs in the one direction. In the other direction, the simulation generates 3 Hall signals and a temperature sensor, and it controls the speed, for example, over UART interface. So on an electrical level, that's a recording of a small portion of a test run. Here you see in detail the block commutation of the PWMs of the system under test. The test system in return generates the Hall signals as digital outputs, and that's the control of the speed done with UART. Here, a little bit bigger picture. Again, the PWMs. Here, the speed changes over UART. Here you see the Hall signals are following, are getting slower and faster. And here we have the analog value for the temperature sensor. So we simulate the temperature sensor, in this case with an analog output, with a DAC. It could also be a digital signal over SPI, I2C, or whatever it is. And the last curve here is just to get the correlation between the simulation model and what happens in your test. We have here the simulated motor speed as an analog output on the board to get the correlation between what the simulation thinks and what happens on the signal level here. So example for a test case is I change the speed over UART. The speed goes down in the PWM. The Hall signals follow here because it's a closed loop motor simulation. That's easier to read than the Hall signals here. Then the next example or test case would be a complete shutdown of the motor. When the temperature gets low, here the temperature gets too low, so the motor shuts down the PWM signals within 100 microseconds, for example. We measure this, say, okay, it needs to be stopped for a couple, I don't know, for half a second or something like this. Then we recover again. Then we make a limp home functionality. So we have a warning temperature in this case, so that the motor slows down. It's not supposed to stop, it's supposed to slow down, maybe to lower the temperature or to get into a stable situation again. And in the end, I want to test explicitly the shutdown, the recovery behavior after a complete shutdown of the motor. So those are the type of things you can do with an integration test, hardware, software, in the integration test for a motor control system. So now let's jump into the demo. I'm going to switch to my development environment. That's in this case an Eclipse-based environment where we can model the complete test system. So everything in this box is generated, compiled, and flashed to my test system. So we're talking about the test system now. Here we have the system under test. That's a manual C code that runs a motor control. That's something I want to test. So let's start with the I/O level. Here on the I/O level, we have the analog, digital adapters, UART. Here the duty capture unit that captures the 3 duty cycles, measures them, propagates it to the motor simulation. The motor simulation runs on every duty cycle. It runs the motor simulation, calculates the new speed, generates the new speed, and propagates it to the whole generator. And the whole generator generates the whole signals at this digital outputs according to the speed. So that's the I/O level. Most of this I/O level is delivered. Some things are special. For example, if you have a specialized I2C or SPI protocol, yeah, you need to adapt this, of course, to your specialized protocol. Things like digital, analog, UART are pretty much standard, so you can use the adapters we provide here. And yeah, we have also examples, of course, for other interfaces and adapters. And here you have the simulation level. Temperature simulation is pretty straightforward. Celsius in, analog value out, 3.3 or 5 volt analog values. Here you can see that's the analog port 1. That's basically this red cable here. That's here we have 16 analog outputs to stimulate the motors, for example. And here we have the motor simulation. You can put in manual C code. You can put in generated Simulink models. If you already have a plant simulation for your Simulink model, you can integrate this here. And you also can use this modeling environment to create state machines, hierarchical state machines. And in this case, we have a state-based simulation. So if the PWM changes, you get a new duty cycle. We memorize the actual duty, and then we calculate in this step, in this state here, the new speed and propagate this new speed to the whole generator. So that's the interface to the whole generator. So here you see all the commands you have for the whole generator. We can change the speed and we can set the direction. In this way, for example, you can do a failure injection and break the system and see what happens, what your control system, whether it detects the error or not. So that's a typical simulation. So now we have the I/O level and the simulations, and now we need test cases, because now your system really can work. So you can start the motor, all the sensors are satisfied with the right values, and the motor works, so the simulated motor works. Now we need test cases. We could now generate the test cases out of the state machines. So the state machines are generated also in C code. But a state machine is not the optimal language for a test case, because it gets really big if you describe test cases. So similar state machine has other purposes, but we still need the test behavior. So that's why we have another language, behavior language inside here, and that's our test language. It's called Cage, for case generator. Usually you start on a level of with your steps. So a step is an atomic test step, if you will. You can create actions and reactions, asynchronous reactions actually, because for example, if I want to change the speed, I create a step request speed. So I send a speed request over the UART here in this case. I expect an answer from my UART that it's been sent, and I expect an answer from the system under test. It's a mirror answer, a mirror protocol that it accepted the command. And they also could come in a different order. In this case, I could put them in the same reaction block then, we collect all the information and evaluate it at the end. But you can also enforce the order. The important thing is here, the timeout is enforced because if you have a reaction block, an asynchronous reaction block, you always need a timeout because your test case could get stuck in case of an error. But you want to continue your test system to work. So, and that's something we can enforce in the test case because we know it's a test case. And you also will not find any messages here for the test case because we can completely generate all the messages needed because we know it's a test case and we know the expectations. So we generate also all the error messages and all the values and so on. So you do not have to take care of that. So now here on the right side, you can see we always generate a sequence diagram for us as human beings to understand better what the test step does. For a test step, that's pretty simple. So you don't need it really for a test step. You can also understand this here. But if you move one level up, you can integrate all the test steps to sequences. For example, here the request speed, for example, the request speed test, that consists of several steps, and you also can integrate sequences to higher level sequences and so on. For example, here I have a test case that integrates several steps and sequences, and they themselves integrate other steps and so on. And here you see always the flat world, because here on this level you can develop things, reuse them and so on. But to understand a test case, really, sometimes you really need the context. What happened before, what will happen after. So that's the level where we discuss things. So now we have created the test sequences, and in the end, we integrate them into test suites. For example, in this case, that's my motor control test suite that tests everything related to the motor control. We also can do combinatorial tests to really break your system. If you want robustness tests, we also can generate combinatorial test cases, but that's a story for another day maybe. Now we have the complete simulation and the complete test cases modeled. You can also integrate manual C code if you have a protocol or something like this, but the driving factor here is the model. And now we can generate this directly here from the environment, also on command line, so that it's capable to run on continuous integration as well. Now I'm going to show you how to run the system from a graphical user interface. That's the first step. I'm connecting with the system under test, and I will break the system by pulling a cable out. So I'm running the test now. I'm pulling the cable out. So let's pull this out and repair it again. So now you see I broke the system, of course, in hardware. And here on the right side, you see the results. So you see here, for example, this test failed. We got on timeout for the UART send. That's clear because I really did break the UART cable. And here you see, if you click on the test result, you get exactly the position in your test model where the system failed. So, and now I said, and that's my last example, I said you can run this on a continuous integration server. So let's deconnect the graphical user interface. I have a local continuous integration server running here. That's a Jenkins server in this case. Can be any kind of continuous integration server, doesn't really matter. The Git monitor, the local Git monitor is monitored here. Git repository is monitored. So I'm going to the system under test now. That's manual C code. I'm breaking this, for example, by setting the duty cycle to a constant duty cycle. So this should have an effect on my system. So I'm going to commit the bug to my Git repository. And here on the right side, you will see immediately that the continuous integration server detects the change and starts the, checks out now the code, builds the code, flashes it, and runs the test. Doesn't matter whether you change the test or the test system. Now, when it flashes, you will see here, you see the blinking of the LEDs. Now the test system is flashed. The system under test is flashed now. It also blinked, and now the tests are running. So the motor simulation and the tests are running on the board. So here you see the text log. That's not so interesting. Just if you need more details, you can have a look at this. And here now you can see the results. So in this case, I will get an email that my system is unstable. I have yellow result here. So that means my test cases, some test cases failed. The last test result here is, for example, the motor control system failed. I get the values and so on. So I've been outside the limits of my system. That's okay, because I broke the system. And in the end, I want to know where it failed. So I click on the traces now on the continuous integration server. I click on the expected failed, and here in my development environment, I jumps exactly to the position where the problem occurred. So that was the demo. I hope it was interesting for you. If you have any questions, don't hesitate to contact me directly via my email, or also under the our webpage. So the Mini-Hill test system is sitting on top of eTrice. That's an open source project also run by us. So part of the test solution is open source. If you have any question, please contact me. I hope it was interesting for you. And yeah, I wish you Merry Christmas and a Happy New Year. Hope to see you next year.